running out to figure out if something is going wrong. Okay, I have this big got it. Okay, good, that worked. So, well, I say my background is a little bit different than yours probably. So whenever I say something which sounds particularly wrong or it's not clear, just feel free to stop and see what's coming here. So the main aim of today's lecture is really to confuse you, hopefully in a healthy way. So you may have some questions on how things look from the other side, and maybe it means to go and investigate them. So why software engineers cares about probabilistic programs? Well, really, most of the applications that you use every day have to deal with some kind of uncertainty. For example, your maps, where every time your phone is trying to localize you, it's not really one point. It's a sensor is producing something which is a little bit weird, like possible locations, some uncertainty, accuracy, information's there, and software has to make sense of it. Speech recognition, every time you ask your favorite assistant a question, the assistant needs to figure out what you're actually talking about, and that's not easy. We do not have like a very precise algorithm to do that, and often we rely on a lot of uncertainties there. Robots, every time you write controllers for robots, of course, you need to take into account that sensors are limited, there is always noise, you cannot measure everything. Some kind of predictions and planning are going to be off, whatever off means actually in this case. You saw yesterday a little bit about finance, so I'm sure algorithmic trading is something that may be teasing in this type of things, but also more practical stuff, like for example, A/B testing. A/B testing, for those of you who are not familiar, is how we work, how we optimize and, let's say, improve many applications which are for mass distribution. If I open Google and you open Google, what they see may be different than what you see. So they continuously run experiments to see what colors, what font size, what position of buttons is the most effective for their goals. And this is called A/B testing. So they literally partition the user base into different like classes or groups, and see to each of them they assign one possible conjecture, if you want to think in a probabilistic terms, and then they evaluate which one is more effective for their business goals. So this is done continuously. Every time you open a website, I mean, say complicated website, they do it continuously. At some point, I think Google was running 67 experiments to decide the color of the font. I'm closing the windows because neighbors are getting noisy. Work from home setting. Just a second. It's good to see people outside in the park, but sometimes it's not. Okay, well, of course, there are basic algorithms which are always there. Like every time you want to implement something which is like for Monte Carlo integrations or this type of software, you of course need to deal with formal uncertainty. Machine learning is dominant, like if you want a great example where these things go wrong, but we also apply them in a lot of things, like game engines have a lot of uncertainty inside. Every time we want to do some facial recognition and realizing what the user is doing, all this software is already using a lot of uncertainty inside this, dealing with uncertainty. And probabilistic programming is a kind of way of championing of helping developers to do their job. So to take the map example, well, this is kind of trivial. I think at this point I spoiled most of it. So what kind of data do we get from the sensors? You don't get really one number, one position, one certainty. You always get some form of approximation, some form of uncertainty. How do you interpret the data? So when you get this data, what's going to happen? What are you going to do about it? And in the end, you want to come up with the guess of where the user is. So, well, this is the kind of process that we think in a programmatic way. So we gather the data, we interpret them, we try to make a guess. Data are called usually observations in this, so just to set some jargon. The interpretation goes through a model of something, and we try to make some form of inference. This specific example actually is not just purely random. You may have heard of a probabilistic programming language called Pyro, which is developed by Uber. Uber is the kind of taxi car hiring company. They developed their own probabilistic programming language because they have very serious inference problems. Well, when you think about GPS, if you are in a city, for example, where most of the customers probably are, you have a lot of noise that comes from the shape of the buildings. If you have tall buildings, for example, on a street, you may have a lot of troubles, and locating a user in one block or another block may make a huge difference, especially if there is traffic or one-way paths. So they ended up developing their own probabilistic programming system. So it's optimized on some form of models, which, for example, include not only the sensor data, like it's a Gaussian on 3 dimensions and so on, but also, for example, the shape of the buildings around it. There are 3D maps for most main cities in the world, and you can include this type of information inside your model. So the definition of model can be very broad and very complex. It's not just a Gaussian distributions or something similar. We will focus on relatively simple things today, but it can be pretty tricky. And of course, then the final monster is inference. I say final monster because often most of the code that you write is for inference, and that's pretty tricky. So, well, just to give you a sense of how difficult sometimes is. So let's say that I take this example from thinking fast and slow. If for a period of 1 year, you have a large hospital and a small hospital, and each of them records the number of days where more than 60% of the babies born are boys. Which hospital do you think recorded more such days? The large hospital, the small hospital? Is it about the same? Who is for A? Joaquin is for A. Somebody is for B? Don't be shy. Somebody is for C? Okay, I got the C. Okay, Matt is for C. So tell me, why do you think it's C? One of you. Again, don't be shy, it's really informal. If you say something that you're not happy about, we can always not publish it. Don't worry.
Hello, I think it would be the smaller hospital.
Can you tell me why?
Because I think if you have a smaller number of babies being born, then the same fluctuation in terms of numbers will be a bigger percentage-wise.
So you're saying that if it's smaller, it's more likely to, you have fewer samples, it's more likely to observe a deviation from the baseline model?
Yes.
What's the baseline model?
50-50.
That's only in your own knowledge. And actually, that's the correct answer in this case, but it's actually, it needs to be explained by saying that in your mind, you're assuming that boys and girls are 50-50. In reality, depending on what's behind the scenes, it could be different. If in your assumptions you say that boys are normally 60% of the population, or the newborn children everywhere, well, in that case, maybe the larger hospital is closer to the expected baseline distribution. So modeling is not easy. The purpose of the question, actually taken from, it's a great book, actually, I recommend it. It's to show that in our mind, we always have some form of models. Just these models are implicit somehow. You never wrote anywhere, I never told you that it's 50-50, the basic distribution. However, when you are going into facing this problem, you gave the correct answer based on the assumption that it's 50-50. So modeling is not easy. There are always a lot of things which happen in our own brain, and it's very difficult to translate into a program. So the program may not know about them, and even for us, it could be difficult to embed them. So modeling is not an easy thing. It's actually an art. And in fact, somebody said that, well, all models are wrong, but some of them are useful. So that's from PhD comics, you may probably identify into this type of game. So is the left model better than the right one? It really depends on what you're going to use it for. And definitely, in this case, say the right one is making explicit to how the supervisor as a professor is seeing you, like a brain on a stick. This is not to be detrimental about the professors, but essentially what you are modeling every time you decide to make a model includes needs necessarily to make some assumption, needs necessarily to filter, to decide what you want to elicit, what is relevant for you. And this process is very complicated. It's a process that starts in your brain, and then eventually you need to translate that into the program. So the program needs to be able to reproduce what you're thinking, which is not easy at all. So in general, there are a couple of ways of thinking, there are many ways actually to think about knowledge and uncertainty, but I will just pick one here, which is let's say what is happening, the phenomena that we observe are based on some kind of structure about it. So there is a structure in the phenomena which is under it. For example, in the previous case, we are assuming that there is a 50-50 distribution, which could be correct or incorrect, but it's kind of our assumption. Then there is also in the knowledge process, you are assuming that you make a number of samples and you observe some variation around those. The actual estimated you probably never converge, and you're also assuming that fewer samples lead to limited convergence, and this brings in the uncertainty. So the kind of uncertainty that I showed you in that example is an uncertainty, if you want, in a frequentist way. You took a few samples, and you know that there's going to be confidence interval, and this confidence interval is probably going to be broader for fewer samples. So thinking and coding into your program, into your design thought both the knowledge, so what is like the structure of the word that you are considering, and how the structure of the word will help you to make sense of the uncertainty, which is going to be embedded there, it needs to be explicit, is kind of a core design issue. We're talking about, in this case, engineering, but you can adapt to many other cases. So the kind of words here that conflate are two. Like in programming, when you write a program, typically you have parameters or inputs which comes into your program, are provided by the users, are read from somewhere. You execute your program with those inputs and you get an output. That's the flow that we typically follow. If you think about statistics, you kind of go the other way around. So you start with data somehow. You have some model that helps you to make sense of those data. So the structure of the word that you're assuming there. And given that, you come up with some conclusions. So probabilistic programs tend to go into writing a program in code, so as you would do in programming, but in a way that it allows you to encode inference in some way. You give a program, programs define the structure, you give the observations, which are the data which are there, and you use them to reduce your uncertainty about things that are explicitly uncertain. So they are specified inside the program, typically parameters. And you try to get the best you can, given your knowledge of the word, the structure in the program, and the data you observed. So to become more practical, the basic definition of probabilistic programming is probably disappointing. So essentially they are programs, any kind of programs, functional, imperative, object-oriented, whatever you want to do, which have the ability to draw values at random. So they have random generators of some sort, but also they have the second feature, which is the ability to conditions on observations. So if you give them data and you say, look, I told you that's a structure, but this is what I observe. What can I infer about the structure? How can I update my knowledge of the word? And more, the reason why we care about announcing programs here are, well, there are many goals. I will pick three here. So one of them is to make uncertainty a first-class element. So we discussed that your conclusion, for example, about the problem before, but many others, is based on some knowledge, some source of uncertainties. For example, what can go wrong, like what can go wrong in the process of sampling, when there could be the uncertainties, what are the parameters, like the ratio in this case of boys that you're considering. And all these things can be like, if you write a piece of code that simulates it, it can get lost. You may have a simulator that generates data, and then you look at this data and you try to make statistics out of it. It's relatively tricky to make explicit what you are assuming to be uncertainty, sources of uncertainty, and structure inside your system. The second big goal is to commodify inference. One of the most tricky problems in statistics is actually inference. And hopefully we'll have time to see an example. But in many cases, when you write something, you spend 90% of your time to get the code that performs inference right. And then maybe 10% of the time is to actually get, let's say, the parameters of the models of your simulation. All of this in the end goes into increasing productivity. Productivity does not only mean that you write fewer lines of code to get the result, but also that you minimize the errors you can make, for example. So you can communicate much better to other developers or to other people what you mean by that piece of code. Okay, imagine, just to give you like a crazy example, imagine writing your favorite program in assembler and showing assembler where the semantic, like if you want the level of the expression of the language is very low, so you're talking to a CPU, rather than writing in Python, for example, where you're writing, you think that you're writing for the computer, which is of course one of the goals, but you're also writing for other people to read your code and understand what you want to say. So when you make uncertainty and models a first-class element, it's readable. So when you look at it, you see a Gaussian. You don't see a number which has been generated through some weird algorithm to resemble a Gaussian. Okay, all of this increase productivity. Less code, less error, more readability. This is all more maintainability. This is all important. So practically though, software engineering, so probabilistic programming language came from different, I would call them tribes in the world, in the research world. So there are some that comes from programming language community, like here you can see Figaro, some of them maybe this needs to be updated and adapted from Frank's book Keynote. Some comes from AI, for example, Problog, which is the way of expressing logic constraints with some probabilistic weights. Others come from machine learning. They're probably some of the most popular nowadays, like probably we need to extend this with Pyro or many of these new sophisticated font probabilistic programming language for machine learning, or from statistics, like maybe the most popular is Standia, which was designed to do statistics in the medical domain, is optimized in that direction. Depending where they come from, they may have completely different perspective on the problem. Some of them will focus on having the language to be extremely general. You can analyze everything and including probabilistic aspect. Others tend to be, I'm on the left extreme. If you go on the right extreme, they tend to say, look, this is just syntax to write statistical inference. You cannot write a for loop. You cannot write a recursive function. And this is probably the full spectrum. We will see expressiveness versus computational power or efficiency. We will discuss briefly about that. So the challenge in machine learning, because I suppose this is probably closer to the purpose of the goal, is how to write a Bayesian model in code. So this is an example adapted from a talk. In 2010, how would you write a paper? Well, you write down the generative model, and this you should take limited time. That's what you have in mind already. You need to translate it there. Then you get 2 grad students, like I suppose most of you, to implement inference for a month. That's going to be the tricky part. You need to get the numbers right. And then use a lot of technical inference to pad out for the paper. I actually picked one example paper to see how this looks like. Well, in 2021, this should be different. The first step is going to be the same. This is where your brain jumps in. You need to get the knowledge of the process which is there. You need to get a filter or lenses that could make sense of the data you observe. But then you should not waste 1 month doing it. You just commodify, automatize inference if you want. And of course, you can spend now the 4 pages of the paper to discuss strengths and weaknesses of the model instead of bothering people with why you decided to get this for loop outside the other to make it faster, numerically more stable. So that's the challenge on that side. From the programming language software engineering side, we will touch on some of them. Well, what do you need in a programming language? What kind of functions or constructs do I need to give you? I would specify the semantics. So semantics is the meaning. When you write code, you're writing according to a syntax, which comes from a grammar. It's the same thing as natural language, if you want, much simpler though than natural language. But then we need to attribute a semantics. A semantics means how do I translate your line of code into operations of the CPU or operation of the GPU. Okay, this is not trivial to do for probabilistic programs. What does it mean for a program to be correct? If is it correct 99% of the times, is that correct enough? That's pretty tricky. When we have probabilistic programming, we will see there are many troubles there to make it fast. So we know a lot about optimizing programs to be fast. What can we do about probabilistic programs? This is a completely different problem, actually. And well, you wrote it. How do you know it's right? Okay, that's going to be very tricky. And there are plenty more challenges. We may touch upon some of them. But before getting to at least one relatively general way of implementing probabilistic programming systems, a probabilistic programming system is probabilistic programming language plus the runtime in which we perform the inference and so on. I make a micro detour into Bayesian statistics. Hopefully I won't be too boring, but it's really basic. So it's about the mindset. This example was irresistible since we have many astrophysics here. So we have these super fancy systems that can tell you whether the sun has gone over. That is actually correct, but before answering, it will flip a die, 2 dice, and if it comes up with 2 6, it lies. Otherwise, it tells the truth. So now, you push the button, it tells you yes. What can you conclude about that? Is it really gone nova or not? Well, if you just based on, say, the basic intuition of observing only the data without any prior knowledge, without any structure which is in your brain, well, you can conclude that probably it did explode. Probability of a random choice of a false answer is going to be like 0.027 there. So really, it's unlikely to happen. But in reality, if you start bringing in your knowledge, well, then you can make a bet and say, well, probably did it. So I will try to explain you like this kind of mindset, and that you will translate that into code tomorrow and in the coming days. So using this poker chips example. So if I have a bag of poker chips and some are blue, others are white, you have no reason to suppose they're the same number or not. I ask you the questions, what is the probability of the first one being blue? And you need to give me a number. And what's this number? What is it based on? You can take many observations here. So we have no reason to suppose they're an equal number, but you also have no reason to suppose the opposite. So you may say, well, probably it's 50-50. Who knows? If I tell you that now the first 10 rows came up with 8 blue and 2 white, is it gonna change? So the trick here is that we are trying to reduce, by observing the data, some epistemic uncertainty about the parameter in this case, which is the proportion of blue chips. every time you think in Bayesian sense, it's not the statistics on the data. It doesn't matter the frequency. What you are caring about is you have a state of knowledge. Initially, you think they could be 50-50. You could be wrong, you could be right, it doesn't matter, but you embed into the structure of the world some assumption that you think are reasonable. Then you challenge those assumptions against the data and you try to rank them to see which one is more reasonable. So I spoiled this one. Let's go. So what could be reasonable conjecture? Let's say that there are 4 chips in the bag. Okay, you have no idea about what they are. And what could be conjectures? Well, it could be any proportion. There could be 4 white. There could be 1 blue, 3 white, 2 blue, 3 blue, 4 blue. Okay, so this is actually exhaustive. It's a very simple problem in which you can exhaustively go through all the possible conjectures. These are all words that you think, because of your knowledge of the phenomena, that they are reasonable, they exist. You can give different weights to each of them. Let's assume that you do not have any reason to suppose that there are more blue than white, for example, so we give the same probability to each of them. So a priori, it's any of them. Now I give you data and I tell you that we observed in 3, just to make it compact, 2 blues and 1 white. How are you going through deciding what of your conjecture is more valuable than the other? You start by saying these are all the possible words, and they all have the same weight and without preference among them. You may have a preference, but let's say that we don't. But after this observation, how can you change your preference about that? Well, the simplest way, the core of Bayesian statistics, you will see it then much more formally in much more mathsy terms, but the core idea is that you want to care about in how many ways each of the possible conjectures can explain the data. And the one that can explain in more ways is the more likely, more plausible, actually. So, for example, in how many ways can we produce that sequence if we have all white? 0 ways. There's no way because we observe 2 blue, so certainly they cannot be all 4 white. Similarly, they cannot be all 4 blue because we have at least 1 white there. And for all the other combinations, there are different ways in which you can produce them. When you compute the different ways, you will again expand a little bit more on the math, but the core is, well, you can reason about each of the draws there. In how many ways can you produce the first row? 0. In how many ways can you produce the second one? 4. In how many ways can you produce the third one? 0. Sorry, I forgot to tell you, you put back the chip every time. Okay, so if you multiply those independent events, you're gonna get if you want the plausibility score, let's call it this way, like counting in how many ways the conjecture can explain the data. Okay, and this is, if you want to go a little bit more formally, it's based essentially on the product real probability. This will be the core of your Friday lecture, if I remember correctly. So how do you go about modeling the world? You have an idea. This idea assumes everything you consider possible. You may have some preference among all those possibilities, and then you challenge the possibilities against the data. How do you challenge them? Well, for each of them, you try to see in how many different ways can it explain the data you observe. The one with more ways is the more plausible. Okay, so this is Bayesian probability, say, for dummies. In a more general sense, what we have done here is that we thought about the model, and the model is, well, it's 4 chips in a bag. It could be all white, all blue, or anything in between. And so this is our conjecture. Then we condition on the data, okay, which allows us to update the plausibility of them, of each of the possible conjectures. And, well, then we see if it makes sense or doesn't make sense. Don't forget that whatever you write in your probabilistic programs, they are not going to tell you if you're right or wrong. Okay, they might sometimes tell you if you've done some types of error. They may help you understand if there was some convergence problem, for example. They may help you understand if some sampling didn't go well, or if you should do more. But whether what you produce makes sense or not, in the end, it's in your brain. Okay, so always you need to critique whatever happens, and then go back and refine your model and go back again in conditioning. The final word is a human word. It should be principled. It should be your rigorous assessment of what you are concluding out of those data and those models. So we will focus mostly on the first 2 points here. How do you design the model and then code in the program? And how does the program, or probabilistic programming system in this case, implement this form of inference when we try to rebalance the plausibility of the different conjectures based on the data you observed? So, well, if you want to get a nice reading, Statistical Rethinking, I think it's a very nice book to explain. So if you want to go more systematically, what we have done is can be formalized into a process. The process is that you want a model. This model includes the variable. which are of two types: data, which is either given or observed. So these are variables for which you know something. For example, I told you that there are 4 chips in the bag. I told you after an observation, so that I draw 3 samples and I got blue, white, blue. So these are one type of variables that you have in your program. The other type are parameters. In this case, could be the proportion of blue ones, blue chips in the bag. They are unknown in general. Then you need to link them. So data needs to be linked to parameters. So there is a way of thinking about it. So it's what we have done before. Like if you have all white chips, there's no way that you're going to see blue, white, blue. But if you have, let's say, only one blue, well, then you can get exactly to the likelihood of observing that sample. So you can just count in how many ways you can generate each of the draws. And there is also another implicit aspect, which we took it implicitly there, is that you can also give weights to the different conjectures. So those conjectures may be more or less likely based on your experience, based on your knowledge of the process, for example. It could be that the factory told you, look, we put more blue chips than white ones, but there is at least one blue. Well, this will allow you like to reweight your conjectures even before observing the data. Okay, so these are all the ingredients that you will need for a Bayesian process. And these are also the ingredients that you will use to encode your Bayesian process inside the probabilistic programming language. So the final goal, of course, is that given all these ingredients that you gave it, you push the button, and the probabilistic programming system should give you the posterior. The posterior is, after I observe the data, I connect them to the prior, how am I going to update my knowledge? Okay, so what is the most likely explanation, for example? Okay. So let's see here. Let's go a little bit more mathsy, so you're happier, I suppose. So if you want to be a little bit more formal, so instead of expanding entirely like on everything that we observe, we can use mathematical objects to make this more compact and more precise. So the variables that we have here are the number of chips which are drawn. There will be a certain number out of n, which is the blue chips that we observe to the draws. And then there will be a proportion of blue chips, which is the parameter that we want to estimate. So we have data that can be observed or unknown, and you have parameters which cannot be observed directly. Okay, you need to infer information about the proportion of blue chips, but you cannot measure it directly, otherwise it would be easy. Okay, that's easy. I know that in physics that measuring is not easy. Don't take me wrong, but that's what you want to infer. Okay, so let's see what the other bits are here. Well, likelihood, I'm just going very quickly here. It's a probability, it's a relative count that we saw before, essentially. So if you make an assumption, any of them, for each of those assumptions, like how many blue chips are in the bag, for example, you should be able to, given a draw, so the sample that you collect, to say how likely it would be to observe that sample. Okay, this is going to be your score. This is the most important measure that like make inference complicated if you want. So in how many ways can we do that? I will go really quickly here, but I mean, if you assume that the proportion is P, well, getting one blue chip is going to be probability P and 1 minus P for one white, and again, P for blue. You can compute that. You need to remember that, of course, that the order doesn't matter. We say that every sample is independent, so it doesn't matter if you saw blue, white, blue, or 2 blues and 1 white, or 1 white, 2 blues. Doesn't really matter the order. So you need to consider all of them. And again, I'm going quickly, but you can rebuild the formula very easily. What you are going to do here, I don't know what's happening to my computer. Okay. It got somehow stuck. The formula that you're going to see there is essentially the binomial distribution. Okay, the binomial distribution will tell you what's the probability of observing a blue, given that you have a total number of sample n, which we say it's given in this case, and your conjecture about P. So P is going to be like the value of P. If P were 0.5, what's the probability of observing blue? Okay, and it's literally counting. In discrete distribution, so it's very easy to trace back to counting. You have data here, you have the parameter you want to infer, and what is missing here is a prior model on that. So what do you think P could be at the beginning? This prior model, again, it gets philosophical, so you will ask a lot of questions on Friday, but it really represents your brain, what you have in mind. 50-50 between males and females is your prior model. Okay, you should try to make it explicit here. It's a good exercise to make explicit all the assumptions you have in this case. Say that we do not have any preference for any value of P, we're going to say it's uniform between 0 and 1. So our main thing, we want to infer information about this proportion of blue chips. initially, we have no preference between 0 and 1. We only know it's between 0 and 1. That's important because whatever you cut out giving probability 0 is certainly not going to happen. When you work out the math on Friday, you will see why. So it's very important to cover the domain. The specific distribution comes to your mind. There is no correct prior. There is no incorrect prior. Okay. There are some which are maybe closer to what you will see later on. So your knowledge was, if you want, more consistent with the reality you're going to observe. So it could make things faster or slower, but really that's your initial state of knowledge. And the initial state of knowledge needs to be updated through the data. And to do that, you create a likelihood. So you use this B, which is a binomial linking. So you're linking the P, which is your parameter. So the knowledge about your parameter will be P is a distribution, of course, it's the result of the distribution, as you see here. If I'm confusing you too much, let me know. So the posterior probability just goes through famous Bayes theorem. I will put here all the bits and pieces and then we'll get there. So that the prior is, you do not know anything about P, but it's not really true. You always know something, you're assuming something about it, at least the domain, probably also the distribution of it, and that's how you're embedding your initial knowledge, that's B. Now, when you observe data, A, well, how likely is the data to occur given your knowledge? Okay, and this is your plausibility. It's the count that we saw before. In how many ways your a conjecture on B can, on the value of P, so encoded in the distribution of B, I should use different letters, can explain the data A that you observe. Okay, and since you have like all this plausibility index, they do not add up to 1, you just add the normalization constants at the bottom. Okay, in most cases, you don't care about that normalization constant. What you want to do is to rank different possible outcomes. Like if you have many possible conjectures, you just want to know which one is the most plausible given the data. That's actually very important because it will explain why, for example, methods like Markov chain Monte Carlo would work. So effectively, what you're doing is prior times likelihood. Prior is your conjecture. Likelihood is how likely is the observation given your conjecture. And then you normalize. We don't care much about normalization at the moment. But hopefully this thought process is meaningful somehow. We don't care too much. I will show you just in a sequence of slides. I can share with, I think I can with you some Jupyter notebooks so you can try these things from first principle and then see how they look in a probabilistic program. So let's say that initially we say that you have no preference. It's going to be whatever number is not normalized here. So you're not seeing actually distribution. It's between 0 and 1, whatever number is fine. Okay. Assuming we know nothing, I mean, this is not correct. You are saying that it's uniform. You cannot assume nothing. Okay. And again, questions for Friday. How do we pick a prior? So you start observing data, you see a blue chip. Well, all of a sudden, the probability of P going towards 1 is going to be higher somehow. You can actually measure, given our model, you can actually exactly measure this distribution. I'll give you the code to play with it. If we observe a white now, well, that's probably going to go down. It's not going to be 1 anymore because definitely there is a white, so it's not possible to roll blue. And then you keep observing. And the more you observe, the more you adjust this prior. So this knowledge. The prior gets updated as a posterior. You add new data. This is your new prior, which will get updated. Okay, so the terms prior and posterior are probably sometimes confusing. It's just a state of knowledge. State of knowledge before an observation, state of knowledge after an observation. Then you add another observation, you get a new state of knowledge. Okay, so that's how we describe what we know, everything we know about B. It's not a number, it's a distribution in this case. It has a domain, so it's a support. It has a distribution of it. Okay, so this fancy procedure, I mean, probably we should not waste too much time. You still see my screen, right? Hopefully.
Yeah. Yes.
We will not spend too much time here, but you can literally simulate it. Like I will give you the code and you can play with it. You can simulate, put the frequencies just for comparison, and then you can literally go and formulate conjectures. So here we are doing nothing really special. We are just formulating a conjecture about how many blue chips are in there. It could be between 0 and 4. And what it does, this function, is just literally see all the possible combinations you can extract there and count in how many ways you can do it. So we saw that if you observe blue, white, blue, as in the slide, you assume there are 0 chips. That's your conjecture. That's not possible. You're going to get 0. It's not plausible. Because if you say that there are 0 blue chips, you cannot observe blue, white, blue. Okay, but if you start saying that there is at least one blue chip, well, that's now it's telling you, look, you can do it in 3 ways. You can expand the data, and 2. So these are the same numbers you saw on the slides. So you can play with it and see how it works. And of course, you can generalize it much more here. When you move into using the formula like with the continuous things, you can do exactly the same thing. For example, what we are computing in this case, where the plots you saw on the slides come from, is really encoding that process that we had before in code, just normal code. Okay, so we are saying, well, there are many possible values of P. They are between 0 and 1. I cannot really check all of them because it's infinite, of course, but I can approximate by taking a grid on that range. And that's what we are doing here. Let me see if I can zoom a bit in. Maybe it's more readable. So what I'm doing is that I'm trying a few points in a linear space, in this case, between 0 and 1. And for each of them, I'm literally trying to count using, of course, in this case, the likelihood. What's the likelihood of observing a specific sequence of data, which is the same above, I guess. What I messed up here. Okay. So I'm counting like how many are blue in the data which are in the previous cell. So that's the likelihood. And I'm doing prior, which is my prior knowledge, times likelihood. Prior here is uniform. Okay, so every value has exactly the same value. It's not normalized. If you want to get the actual posterior, you should normalize here, which is what we are doing in the last line. I'm just saying that all of them have the same number. If you put 1, you put 5, you put 10, doesn't really matter. That's your relative score, relative plausibility. If they are all 5, it's like having all of them to 1. So all the possible conjectures are going to be like with the same weight at the beginning. Then you have the data that we had before, and you use the binomial mass function in this case, so the equivalent of likelihood in the discrete. And then that's what you're obtaining here. So it's likelihood posterior, and you go through all this, and you can get all the plots. So we wrote a lot of lines of code which are not necessarily clear. Okay, so there is at some point a binomial coming here. The fact that I called it likelihood helps, but what are all these numbers in this case? If I show you how it looks like in a probabilistic programming language, I picked IMC, it's a popular one, there's nothing really special about it. That's what you would have to write. You're saying how many draws have there been? Please take this example, 9 of them from the last slide. How many blue chips did you observe? 6. Good, tell me something about what you know. Well, what I know is that there is my parameter is the one that I do not know anything. Well, we say that I know something, which is my prior knowledge. Forget about this syntax to make it faster. So I have my prior knowledge is that it's going to be uniform between 0 and 1. That's what I know before observing the data. Good. How do you link it with the data? Well, I have a binomial, which is taking P as a parameter. The number of draws is given, so it's data. And I observe this number of blue chips. Does it look more clear to you? You only write the prior and the likelihood. And of course, the observation, adding them here, or you can do it in other different ways. It's just syntax here. You can ask a lot of things about your model, so you can try to visualize it. You can see what are the dependencies among variables. It may tell you like, these are the random variables, these are the densities. It can tell you a lot of diagnostic things where you can try to look at the model and see if it makes sense. And definitely what you know here is that your conjecture on P is going to affect the number of blue chips you're going to see there. And this goes through a binomial distribution. So when you want to analyze it and try to infer something, well, if you think only about your prior, look, this is what's going to happen. P is kind of uniform almost everywhere. But now, if I give you the data, well, so I just ran all of them before to save time. After the process, you see that your knowledge about the value of P will move from this flat line here, which is your uniform initial one, will move into something which is much more complicated. And you can see these curves here, which are your new distribution or plausibilities, if you want, on the different values of P. And you can see that P here is kind of biased toward 0.607. I don't know what was the actual value. Yeah, no. Well, data here is different. So you can try to run the math itself, like to see like what should be the actual value. But effectively, this is telling you your knowledge before observing the data. Sorry, I'm scrolling too much, which is this prior predictive, as it's called in this language, but every language has its own syntax. It looks like this. It's everything flat between 0 and 1. As soon as you start moving forward, you're going into something more complicated, like I include the data and your knowledge has been updated this way. So now you know that 063 is much more plausible than whatever comes after. Okay. Unfortunately, I am super slow, so I'll tell you very quickly what's happening behind the scenes. So how does
5
it
minutes,
do it?
Antonio?
Okay, good, terrible. Okay, so how can you do that? Analytical solutions are often possible, so we go straight to Markov chain Monte Carlo. So what I can tell you very, very quickly is that when you write probabilistic programs, you are defining a generative model. Okay, and the space of this generative model is not necessarily the domain of the variables that you're trying to sample, but it's the execution trace of your program. Okay, which is called formal execution. So every program has a sequence of random choice. Every time you say x is equal to Gaussian realization of Gaussian of certain values, that's actually a choice that you're doing there. And then you have some conditioning where you say, look, I actually observe this data. So this specific random variable, which is linking my prior knowledge with observations, has to be forced to match this data. So how likely is it to observe? So I will just tell you one challenge and show an example, then we'll skip straight to more conclusions. Our probabilistic programs different than normal, let's say, generative models that you may see in statistics. In statistics, the models tend to have like a kind of fixed structure. So you can say that x is a Gaussian, for example, x1, x2 is another Gaussian, which depends on x. So you have this kind of dependencies. But the structure of the model is relatively simple, meaning that typically you have always the same variables for each time you run your program. You have always the same order and the same type of random decision procedures that you're taking. So it's relatively simple to encode also in, let's say, more efficient graphs. When it comes to a probabilistic program, this is pseudocode. You have weirdo things, like what you see here on the slides. It's actually pretty simple still. But depending on the initial decision that you make on X, you execute your program, you generate X with certain likelihood it's going to be the number 11, for example. Well, if X is larger than 10, so in this case 11, you're going to generate only another random variable, which is a beta and doesn't depend on X. If it's less, well, you're going to generate two random variables in this case. One is Y, which again doesn't depend on X, but the other is Z, which depends on X. So you can encode pretty complicated models into the system. And I won't really go too much into it, but yeah, just very quickly. So with this program, every time you execute one line of the program, you are generating examples. Let's say this x11, in this case, says true. You have a likelihood of generating it, and you update the state of your machine. Now your machine, after executing the first line, knows that Alice did it is 1. So you can drop the else branch because the if will evaluate to true. And again, you sample for a with gun. Say that accidentally you got true, and the likelihood of that outcome is 003. State is going to be A true and W true, so with gun is true. So far, what we are doing is literally sampling from your program, which is executing one instruction at a time. We obtain some information which update your state, and you got these probabilities. This is formulating your conjecture. It's the same thing as saying how many blue chips can be in the bag. Can be 1, 2, 3, 4. Okay. You're doing exactly the same. Your initial possible words includes cases where Alice is true or false, and you give a weight 0.3 where Alice did it is true. Cases in which with gun is true or false, and you give a 3% probability of being true. Okay, this is just your conjectures. Finally, you get this observe statement. Observe is conditioning on data, and it's telling you that with gun must be true. Now we know that with gun existed. So how do you reweight your initial conjectures given the observation? Well, with gun in the current state is true, definitely. So it's fine, which means that this path should add up, should be considered for the execution. Okay, so the path that you selected, this specific conjecture you formulated, has a plausibility index of 0.009. There will be others, for example, where Alice didn't do it, and you will get the with gun with the different values. Okay, all the possible conjectures are formalized in that piece of code, which means effectively we'll decide with which probability you end up in a world where Alice killed somebody with a gun, or Alice did not kill somebody. And again, the probability that somebody was killed with a gun is just generally 80%. This example is adapted, from artificial intelligence and model approach. I forgot to add the quote here. So you are formulating all the possible words by literally simulating them in a piece of code where there is uncertainty explicitly named. Okay, when it comes to observe, you don't care how, but the probabilistic programming system is going to weight all your conjectures and tells you each of them how plausible is against the data. What you will obtain as an output is a distribution on the plausibility of your parameters. Skip, because it's just too long. I was mentioning it was difficult to cut things, but yeah, I can share the slides. This is actually, you can find them in the references. And literally what we are doing when you write the program, you are effectively defining a prior, it's just the probability of generating some data given that your program evolved in a specific way, a specific sequence of steps. This is relatively tricky, but for every trace that you extract, you can get a sample for this F and G, which you can use then to make inference on it. Observe is a very bad beast. We don't care. Simple ways of looking at observe are, well, observe can be handled in two ways. Either you compute the likelihood of the data, or you can use a very subtle trick, which is called rejection sampling, which is, of course, a very standard one, which works this way. Say that you have your initial conjecture on the left side. It's telling you that X is your prior information on the parameter, and it's going to be between 0 and 1. X is linked to the data Y by being the location of the normal distribution of the second line. Okay, so those two lines are prior and likelihood. So they are linking it's your initial knowledge about X and how X is linked to the observation. Now I'm not giving you a specific number for Y, but I'm telling you that Y is positive. How can you encode this? Well, you can either compute that likelihood if you have an explicit form or something which is nice, nicely manageable, or you can fall back into rejection sampling. So what you do is during your execution, you just replace that observe with if the condition is violated, just restart the motor, drop the execution rate. A lot of dense data. I'll give you the slides and you can write me questions in case you have them. Okay, so let's go to the conclusion. So what is interesting here? You can take any program and essentially you can make it probabilistic. You just need the random generators. You need a way to track and control what is generated by those samples. You have a paper in the reference that will tell you how to make your favorite programming language probabilistic. And you can just use rejection sampling, which is very general and works in every case. The problem is that this could be used for any piece of code that you write, but it's possibly very slow. Execution space is huge. There is no way that you are going to sample all the possible execution of the program. Every time you have a while loop, every time you face a condition, you multiply by 2 the number of paths. Okay, so it's an exponential growing the number of paths in the number of conditions you evaluate. So these spaces are huge. So it's very difficult to analyze. If you try to optimize code for execution speed, it's going to be often in conflict with optimizing for inference. So that's another tricky sub. And then you go back into the usual problem. Normal programs do not terminate, make a stack forever. So you do not really have it. It's a nil-defined likelihood distribution. You may not have convergence, for example. The alternative way is to go into domain-specific language. So you restrict what you can write in your program. You cannot write a web application, for example, but you can write some specific, you can use only some specific constraints. Or you can restrict some specific directives. You cannot have while loops, but you can only have for loops with a fixed number of steps. Or yeah, you can do only data preprocessing, or essentially you are aiming into writing math into some code-like thing. This is awesome because most of the language that you're going to see will use this restricted system, not to have a general purpose language that does also probability, but to have a domain-specific language which is tailored to machine learning application, for example, and it's super fast. Skip. I'll give you a couple of references later. Some of the challenge, this is just my point, and then you ask questions. So it's, well, compilers do a lot of cool things. When you write your program, it becomes super fast thanks to your compiler. Compilers can identify, for example, that some code blocks do not need recomputation. When it comes to probabilities, you may embed a new kind of code block summarization. For example, if you're adding to Gaussian, well, you can just avoid generating one, generating the other, adding them, and replace with a single generation from a different reparameterization. These type of things do not exist in regular compilers and need to be added into special ones. If some code is dead, for example, A is an off normal, it's going to be positive. Everything which is in the if branch should not be compiled. You can drop it, which gives you more memory. And you can use a GPU, for example. Differentiation is another tricky part, and parallelization. I won't expand on them. They are probably self-explanatory. Normally, in a program, when you want to see if it's correct, you try to figure out what's the control flow, what can be executed. In a probabilistic program, the question is not what can be executed of your program, which function can be called, but how likely are they to be called, and how much probability must they carry. And that's a very subtle problem, for example. Again, I gave you some references. It's more to confuse you than to clarify all the bits here. Data flow is the same problem. I can ask you, like, at this point, the value x, what kind of distribution can it take? Can it ever be a distribution with something negative? Can it have a mass of less than the 1% into going into a failure or an exception in your program? These things do not exist. Simple execution is the reverse one. Can you give me like some input distribution that will make your program fail? Slicing, I won't touch on it for now. And let's go to the last one. How do you testing? Well, testing probabilistic programming programs is complicated, so you cannot really test them. It's very difficult to come up with an oracle. So the best we can do is to use either cross-validation. So you try the same model difference and different inference should converge to the same point. You can use cross-validation. You can translate from one language to another and see if two different systems converge to the same values. Or you can use what is called semantic preserving transformation. For example, if I take one parameter and I add 0 to the parameter, that's going to be the same. It can be something different. Or if I add the Gaussian noise around some value, in some cases, I may expect that the inference is going to go to the same place. So these are all checks that you can use. And unit testing your specific program, so not the programming system, is going to be a nightmare. You don't know when it's correct, when it's wrong. But you can use things like metamorphic testing. For example, again, if I increase the value of x, do I expect that y should increase too? If you can do that, then you can write a check. Okay, I will close on this one. Termination is not good. Sorry, we are out of time. So you can imagine that termination is a big beast. In general, we do not know if your program is going to get stuck. With probabilistic programs, it gets very fancy. Sometimes it's stuck with probability 0. Sometimes it's stuck with some probability. Sometimes it's not stuck. And it changes like the way we think about computation, also from a semantics and formal viewpoint. Thanks, guys. I won't talk on this, so sorry for being long. Your questions? Right. I know that I can do more than help you.
Yeah, thanks very much, Antonio, for the nice talk. I'm going to stop the recording as people can